I warmly welcome you all to the latest public webinar conducted by IESL EETESC. This is the 10th lecture in the lecture series conducted by the Electrical Electronic Telecommunications Sectional Committee with the aim of sharing the latest engineering knowledge with the public. Today's webinar is titled Robotics for AI for Inspection and Maintenance, Challenges and Opportunities. The session will highlight challenges in inspection and maintenance of industrial assets, as well as robotics and AI for improved efficiency, reliability, and safety. Without further delay, I invite Engineer Viraj Muthugala, Chairman of Electrical Electronic Telecommunications Sectional Committee, to deliver the welcome speech. Over to you, Engineer Viraj.
Thank you, Engineer Kavidu, and good evening, everyone. I warmly welcome you to today's webinar on robotics and AI for inspection and maintenance, and challenges and opportunities. So this webinar is, as Engineer Khan said, it is organized by Electrical, Electronics and Telecommunication Engineering Sectional Committee of IESL. So let me brief. As industries evolve, the integrating robotics and AI into asset management is no longer a choice. So it is a necessity for improving efficiency, reliability, and also safety. So tonight we will look at very closely at real world deployments and trade-offs, and how these systems work alongside with human teams. So to guide us today, we are privileged to have an outstanding expert, Dr. Viraj Muthugala. He is a senior research fellow at Singapore University of Technology and Design. He has a first class electrical engineering graduate, PhD, the bachelor's degree from University of Moratuwa, and at the same time he holds a PhD specializing in robotics and human robot interactions. So I request the audience not to get confused, because resource person and myself for the same name, so don't get confused about that. And also I request all the participants to actively join and ask questions at the QA session at the end of this session. So I invite Dr. Muthugala, and also I thank him for accepting our invitation. So over to you, Dr. Muthugala.
Thank you, Viraj, for introductory briefing, and also thank you very much for the IESL electrical and electronic and telecommunication subsection for organizing this wonderful event. So I will start my presentation with sharing the screen. Is my screen visible?
Yes, we can see the screen.
All right. So in this talk, I will discuss about what are the usage of robots in inspection and maintenance application, and also the challenges and opportunities. I am Viraj Muthugala, currently a senior research fellow in Singapore University of Technology and Design. So briefly, I will introduce about myself and where we are currently working on. So I'm a senior research fellow in Singapore University of Technology and Design. It is simply referred as SUTD. And SUTD is a little bit new university, like established in 2009 with collaboration with MIT. And in SUTD, we have different SUTD is AI and design centric university, where it differ from the traditional university, where in the SUTD we cannot see the department concept. In here we have like a concept called pillars. So I am from the engineering product development pillar. So because of this pillar concept, we can work on multidisciplinary team. Like sometimes we are working with architects, and sometimes we are working with another field experts. Likewise, it make us to do research and development in a more collaborative and interdisciplinary manner. So here you can see, let me change the pointer. Okay. So this is a SUTD University, and here you can see some of our robots. And this you can see a example scenario of doing field trials of a robot in a construction site. So most of our robots I'm going to discuss today, we have done some field validation run in real world environment, and in my talk, most of the insights are discussed here. Okay, in the today agenda of my presentation will be, first I will describe why we require inspection and maintenance systems based on robotics and AI. Then I will discuss about our signature robotic development like reconfigurable tiling robotics. Then about more detail about robot development, deployment and development. Then I will start to discuss about the reality of robotics and AI in today's context. Then I will discuss about the engineering trade-off, and finally what kind of opportunities are still there to pursue. So why inspection and maintenance matter? Like currently there are a lot of buildings and also industrial infrastructure. We require like frequent maintenance and inspection. So typically global infrastructure maintenance expenses are more than a trillion annually. And also this is, if we consider about maintenance cost, it is almost 60 to 80% of the total life cycle cost of an industrial asset like a building or a machinery will be like 60 to 80% of the life cycle cost will be for the maintenance. And also some of these maintenance tasks are high risk. Like if we want to, let's say, inspect facades, then people need to use ropes, either or gondolas to climb those uh, uh, high-rise building and do the inspection task. But those are a little bit dangerous and might lead to safety issues. From the other end, like when sometimes when doing the inspection task, let's say when inspecting maybe a fuel tank of an aircraft, those are very highly confined spaces, and it is very difficult for humans to go through those small confined spaces and inspect them. So therefore, robotics and AI developments are targeted to solve this harder, riskier, and more expensive inspection and maintenance tasks. So now these days these things are a little bit rapidly increasing the use of robot, because now these mainly the robots, if we consider about a robot used for any application, robot need to have some sensors to perceive the environment. Nowadays, because of the development of semiconductor and other technology, now these days the sensors like LiDAR sensors which can use to perceive the obstacles, then depth cameras, then inertial measurement unit, like devices, sensing devices are little bit coming cheaper. And also these days you can see many development of AI technologies like vision system, vision language model, those vision language model can, if we fed the image, it can identify and classify. This is a, for example, if we fed it with a image of an kitchen, it can identify this is a kitchen, this stuff over there. So these things have been rapidly increased in the last few years. Then also in mechanism wise, now in early days we were mainly focused on robots with rigid shape. Nowadays, those are moving toward the reconfigurable mechanism, like robots can change their shape to go through narrow spaces. Some robots use like flexible and soft mechanism to adapt to the environment. So those kind of development in other field like sensor, AI, and also mechanics helps to develop the robotic system in a rapid way. And also from the other end, from the industry, there is a requirement, there is a pull from the industry where clients ask robotic system to solve their issues because of the because the some of the maintenance and inspection tasks are riskier and also dull and difficult to handle. So therefore, there is a lack of human labors to perform those kind of tasks. And also sometimes skilled labor is expensive. Because of those things, there is a pull from the industry side as well. So now I'm going to discuss about our signature platform called Tiling Robotics. I think most of you have played Tetris game. In Tetris game, the shape can deform into 7 different shapes. As you can see here, in the Tetris game, it can change the shape into these 7 different shapes. So, inspiring from that concept, we have developed a robot called HTETRO. So it can reconfigure into 7 different shapes. It has like 4 square shape blocks like this, and then it can reconfigure into these 7 different shapes. So these are when we go first we initially inspired from the Tetris game, then we have looked into the more mathematical formulation of that one. Then we found that these kind of things are typically known in mathematically known as polyominoes. Polyominoes means like those are constructed with uniform polygons connected serially together to make new structures with different number of blocks. So, and these are mainly used in mathematics. These can be found in under tessellation theories. Therefore, we have named these robot class of robots as tiling robots. So, and here you can see the first one use a square shape with 4 blocks. So we can have a robot that can reconfigure into these 7 different shapes. In the next one, we have tried with the this honeycomb shape with the 4 block. It can reconfigure into these 6 different shapes. Then with 3 square shape, we can have these 2 shapes. Then this 3 hexagonal, we can have these 3 shapes. Likewise, when we increase the number of blocks, we can increase it exponentially the number of shape that can produce. So the main advantage of these robots is the robot can change their shape based on the concept. Based on the concept. For example, let's say we use a cleaning robot. So if the robot is fixed shape, it cannot move through narrow spaces. Like if it encounter legs of a chair, it might not be able to go through. But this kind of robot can change its shape and move through it. So that's the simple theory behind the development of this robot. So robot can change the shape based on the polyominoes theories. Then we need to have a control algorithm that can handle this variation of shapes, because if we use this kind of shape and suddenly change to this one, we need to have better controllers. We need to tune the parameters. So we have to have different types of controllers. Then also when we are doing a task like navigating through a narrow space, we need to have a planning layer, which is especially designed for this kind of shape changing robot. Then after developing this robot, we have done real public testing in real public environment. In my slide, next slide is detailed that on. So mainly since this robot can be used for application like maybe cleaning, disinfection, or other inspection task in narrow spaces, because this shape changing ability allow it to go through narrow spaces, and in open areas it can use uh, any other form to do the coverage faster. So the path planning is one of the essential things. So initial days we have explored like this control from classical control to modern AI. Like initially we uh, developed a search-based method like modifying the ESTA algorithm, because ESTA algorithm we can use to find paths, but it is only developed for fixed shape. So we have modified those ESTA algorithm to suit for reconfigurable robot. Then we have experimental with meta heuristic algorithms like genetic algorithm and gray wolf optimization, where we can get optimum decision making. Then we have also explore using convolutional neural network and uh, RRT algorithms for learning based and search based combinations. Then we have also explore use of reinforcement learning, and in these days we are more on exploring use of vision language model for decision making. Like uh, for example, the image is taken by, let's say, ChatGPT, and it analyze which kind of shape it needs to have, then the robot will act according to that. Likewise, this is like now currently we are exploring in modern AI approaches in this path planning of these reconfigurable robots. Here you can see our robot deployed in a real food court in Singapore. We have conducted this trial for 3 months in a public food court. So before moving into the actual food court setting, we have first tested our algorithm inside the laboratory setting. Here you can see this the laboratory setting. So here to move through these narrow spaces, robot use the I shape. And if the space is large, it use this O shape to clean it. Now you can see the usage in the real environment setting. The main problem in the first week when we deploy this robot, the robot wasn't work as we expected. In the lab, it was work very well, but after we deployed into the actual food court, it doesn't work. Because what happened was in our laboratory setting, in indoor setting, the environment flow was well smooth, but as you saw in the video, the flow of the real food course was not that much smooth, and also there are some clean water, and robot need to avoid those kind of things. Then what we do is, instead of like going directly to do the testing in the real uh, outside food court, first we start doing trials in the university canteen. Here you can see the experiment, some experiment and trials conducted at the university canteen. So when it encounters narrow spaces, it changes the shapes to a longitudinal shape like I shape, but in other places it used O shape. Now the other thing is, like in uncontrolled environment like food courts, there are people. Always there will be people, and this kind of objects are placed there. So we need to have like some simple algorithm to solve these kind of things. So in that case, our approach was first classify it is as a human object or an object place, like some kind of a box or some other thing. Like what we do is, robot go to that location and wait for 5 seconds, and if it is not moving, then robot assume it is a some kind of a fully fixed obstacle. And the other thing we done was, like in human, now in the seating settings, in seating location, if somebody sit there, he will not leave for a considerable amount of time. So robot should not wait in that area. So we have divided our environment like into we have divided the environment into two sections, like these are seating areas and these are corridor like environment. So in that area, if robot is doing the cleaning using O shape, because that is more open area, and in this area, robot is doing the coverage using I area. So since this is a cleaning robot, the goal is to maximize the cleaning area. And if an person is detected in the seating area, the robot assume that the person will not move, so it will not wait for that person and move back. Likewise, similarly, we have like run this one with design iteration, and finally we have done this one for almost 3 months in a public food court in Singapore. So main challenges we learned from there is like this environment from laboratory setting to the public environment are high drastically different, like flow condition, the obstacle layout. And typically when we deploy this robot, we need to first create a map. But in this kind of environment, the map in the next day is different because the stall owners change their food uh, carts and those locations. So environment is a little bit different from the what we mapped previously. Then also we need to little bit careful with the public, like people. Sometimes the robot encounter with some people who doesn't like the robot. So that kind of things also we need to cope with the situation. So what we identified was when we are doing planning doing a real world deployment, first we need to test it in laboratory, then we need to do in testing in a semi-controlled environment, then again we need to modify the algorithms, then we need to go to the real world setting and do the one. Likewise, we need to do it in as an iterative process and fine tune our algorithms. Okay, that's about the some development of reconfigurable robots. Now I'm going to discuss about 7 more deployments done on maintenance and inspection robotics. So Estetro, give me a minute. I'm trying to change the pointer. Okay. So Estetro is a staircase climbing robot. So in every building, if it is a multi-story building, even though it has a lift, definitely it will have a staircase. So cleaning of this staircase is also a problem because the cleaners need to climb and clean each steps. So we have developed a robot called Estetro, which is a staircase climbing robot. Initially, we intended it for cleaning the staircase. It is embedded with vision-based detection method. As you can see, it can identify the staircase using the vision-based method, and then after identifying the staircase, okay, it detected the staircase, it measured the step height, riser height, and the step size also using its sensors. Then it used this reconfigurable mechanism to climb the staircase. As you can see, after climbing the first step, it do the sideway movement to clean it. Then again, it consists with like 3 blocks. By changing the one block is in the first step, then the second block will be lifted, then finally the third block. Likewise, it can climb the staircase. This is another version. In the initial version we saw there, it can only climb, but it cannot descend the staircase. This version can do both climbing and descending. And these robots are equipped with LiDAR sensors which can detect the steps and then do the measurement of the step size and the riser size, and then decide how much one block should lift and the other one should how much it should move forward. Likewise, continuously it can descend through and climb through these steps for cleaning application. Apart from cleaning, we have tried using these robots for good carrying, especially in construction situation. Like if there's a building maintenance, if we want to carry out some stuff to the top floor, sometimes use of the normal passenger lift is a little bit difficult. So in that case, how we can carry heavy loads in these kind of robots, we have also tested that kind of things. So the what are the insight is like for this kind of robot, the main important thing is like this robot need to identify the steps clearly and do the change of the step properly. Otherwise, robot might topple down, leading to some dangerous situation like robot might fall into a human. So the AI and its autonomy technology should be robust in detecting these step and the staircase properly. Then we need to have proper control algorithm that avoid the toppling of the robot in situations. So finally, the use of this kind of robot can improve the cleaning efficiency and also typical day-to-day building cleaning tasks. Then I'm going to discuss about some of our robot development targeted for high-rise facade inspection of buildings as well as aircraft fuselage inspections. So we have developed several robots for these inspecting surfaces where the typically humans need to climb to do the either cleaning or inspection task. One of the drawback is the human-based cleaning or the inspection is the safety because human need to climb through ropes or using gondolas, which is not safe. And also finding labor is expensive and also sometimes difficult. So these robots, first one is we call Mantis. It is deployed for glass facade cleaning. So this robot use like as you can see here, it has three module like this. Each module has a vacuum suction mechanism. Because of the vacuum suction mechanism, it can attach to the surface like this because of the vacuum pressure. So the one of the main advantage of our robot over the existing robots with let's say a single module, if we use a single module robot, typically in glass panel like this, we have separators like this based on aluminum or metal. So those separators have some kind of a thickness than the glass. So what happened is if we use a single block, it cannot move through this separator. So here we use this three module mechanism where this first initially when it in a glass panel, all the three modules will be attached, is properly attached to the glass panel. What happened is when it encounter a separation like this, the first module, we switch off the vacuum system and we use a screw mechanism in back of the robot and we lift it. Then still the other two blocks will be attached to the here these two blocks is still attached to the glass frame. Then these two robots start to move toward right. So this one will pass through the separator as you can see in this video. Here please note that this robot is like fully attached to the glass frame and actually these two ropes are only for safety purposes and even we remove these two ropes is robot will be still in the glass, but for safety regulation we have to always use safety ropes when we are using climbing robots. Then as I have explained, now the second module move to the next block. Now it is attaching to the glass panel. Then third module will be moved. So similar, likewise, we can use this mechanism to move from first clean one frame, then use it to move to the next frame, then again clean it, then moves to the next one, again clean. Likewise, we can use this robot to cover large area, and this robot is also equipped with AI-based method to identify the frame and for the autonomous decision making for transition from one plane to another one. So here you can see a aircraft fuselage inspection robot. This robot, the main advantage over other robots is this robot has a reconfiguration mechanism where this robot can change between two different planes. It can in this wings, and then it can move to the fuselage using this reconfiguration. Here, this as I could remember, we have conducted this one in one of the airbase in Singapore, and I cannot remember what is the exact model of this airplane. So as you can see it here, so this reconfiguration allow the robot to move from the wings to the fuselage, and then it can attach to the surface and climb its own. So we have developed like vision-based inspection modules for these robot. Like as I could remember, we have used YOLO-based aircraft crack detection method. We incorporated it with this robot, and after running this robot, we can identify where the scratches are on the surface of the robot, surface of the aeroplane. So here the one of the main point to highlight is the safety is one of the critical things for this climbing robot. But the problem, if we want to try to ensure safety, typically the sometimes autonomy have issues like reliability issues. So sometimes people use teleoperation. Some of these things are teleoperated also. But the problem is if we want to do like scaling, because if we cannot always have a person to operate these kind of robots, so we need to have a autonomous system that can automatically decide, take actions, and if it is losing adhesion, it need to autonomously identify those things and take safety actions. So therefore, it is essential to have autonomy for scaling this. So we have developed methods that can identify if there is a vacuum leakage, and so if there's a vacuum leakage, there is a risk of falling. So we have developed such kind of methods for identifying vacuum leakages and take precautionary actions in the robot operation. Okay, then the next one also another type of climbing robot. This one we developed for ship hull maintenance. Typically, when the ships were in sea for months, there will be biofueling and sometimes the corrosion. So therefore, after several months of sea, they take it to docks and do removing those biofueling and also stripping paint using hydroblasting and sand blasting. This robot we call as uh, hydroblasting robot for ship hull maintenance. So you can see the video. So this is hydroblasting. We have a high pressure hydroblasting device fixed to the robotic arm, and here you can see paint removal in one of I think in Tuas in Singapore Tuas dockyard. So this is the situation of biofueling in this is the real ship, some biofueling, and this is in the ship surface. So we use like magnet based on neodyme and in the wheels of the robot. So this magnetic addition help us to attach this robot to the ship surface. In the previous climbing robots I have explained use like vacuum suction or the thrusters. But the main problem is if we use vacuum for these kind of robots, this hydroblasting also, if we blast the sands or water in this way, there will be repulsive forces in this direction, and typically the air attachment vacuum might not be sufficient for stable. And the other thing is like in ship hull, those are made from iron. which is very good ferromagnetic material. So in wheels of this robot, we use magnets. So it allow us to attach the robot to the ship surface, and then we have this robotic arm that can move like this, and robot will move forward and then zigzag pattern to cover the area for blasting. And also it can also do we have tested it for sand blasting, which is, as you can see here, when doing a sand blasting, it is a very tedious and unhealthy and risky task for human labor. They need to wear PPEs, and also those sand particles are not high health hazard. So use of these kind of robots can elevate the risk of health hazard, as well as we can improve the efficiency, because these robots are equipped with also AI based method where let's for example, when the robot is doing the hydroblasting for corrosion removal, we have developed method that can self-evaluate whether the corrosion is completely removed or not. If it is not removed, it do the hydroblasting little bit more to completely remove it. And the one of the main important thing for this robot is we need to ensure that everywhere is properly blasted. That means we have to ensure coverage of this surface. And when we compare to like cleaning like application in a home, the surface is much more flat surface. But if we consider a ship hull, it is not a it is a vertical shape with some slanted arrangement. So we have to formulate some energy efficient methods for the coverage, and therefore the autonomy and this energy efficiency planning are essential, because nobody will use a robot that use like twice of energy similar to a human. And also the if we consider about a ship hull, it is a very large surface, so a robot need to do it in an efficient way to do the coverage within a given time period. So next robot development is about false ceilings. So false ceilings are everywhere. You can find in office buildings, shopping malls. So one of the problem in false ceiling is all the building infrastructures will be going through those false ceiling, like electrical cabling, HVAC system, pipes, then fire system, water pipes, and those kind of things. And the other problem is it is not capable of climbing through that one by a human, because these are hanging with cables. And also sometimes there can be rodents who have already damaged the wires, which might lead to some electrocutions if somebody trying to access these kind of surfaces. So typically in currently when we before initiating this development, the inspection process in Singapore was done by like people remove one block and then put head inside and then use a torch and see surrounding, and then again open another place and climb it and just see from inside. Likewise, they do the inspection, but we require like routine inspection, because there can be water leakages. If there is a water leakage inside for a long duration, maybe 1 or 2 months, these hardboard sheets might get damaged, and suddenly we do not know until it collapses. And the other things, there can be rodent, which might be issues for kitchens and like things in food court. And also there can be damages to fire system, alarm system. So we have developed this robot called Falcon. Uh, its form factor is very small, and the main advantage is this is a mock setup of an false ceiling. It can climb through these bars which used to connect these kind of things, and also it can climb through these bars, and it can go through wires, because typically inside the environment is unstructured. And the main problem we face is like since this environment is very confined and also unstructured. So it is very complex task to establish autonomy because we don't have much sensing. Sensing is covered, and GPS is not possible for this kind of indoor application. So in this situation, we didn't go with the full autonomy. We have developed it with some shared autonomy where we use interface with an screen where the user can see where the robot is and they can operate the robot direction of movement and those kind of things. So what autonomy do is autonomy identify if there's a leakage, where is the location, those kind of things is identify the autonomy, but some decision making is taken by the humans. So in here we argue that use of the instead of going with a fully autonomous system, we thought of going with a semi-autonomous system where shared autonomy system where robot handle the sensors and some localized navigation tasks, but some tasks like moving directions and those things are handled teleoperated by the human. In this kind of situation, actually it is also worthy because it is very difficult for human to open like 10 places inside a room and climb through the ladder and inspect. Instead of that, a person can only climb one time and put the robot inside and operate it to inspect the whole environment. Then the next development was about Panthera robot. This is a outdoor sweeping robot. So in if we consider about parks and roadside pavement, there are a lot of cleaning requirement. Daily there will be litter like from leaves of trees, sometimes water bottle, polythene, likewise there can be so many litter. So we need to like currently what we do is human cleaners will do the manual cleaning process. So when we go to outdoor, doing the cleaning task in daytime is a little bit difficult and also time consuming. Therefore, we have thought of developing this robot called Panthera. This is a outdoor sweeping robot. And as you can see it here, the robot is typically a little bit weight and size is typically high, is almost maybe half of a car, and it is equipped with multiple LiDAR sensors, as you can see it here, LiDAR sensors, depth cameras, and also for the sonar sensors. Then brake light, because this is considered as in Singapore, this kind of large size of robots are considered as autonomous vehicles. So we need to have brake light, signal lights, and those kind of things also. As you can see it here, the front have two brushes which we can remove and detach. Then those can be ground, and then this is doing the cleaning coverage. And while if there are humans, it can avoid and do the coverage. And here you can see the path planning happening inside the software, and here you can see some cleaning. So here we have equipped with different sensors and detect what kind of leaves there. If it is identify as wet leaves, the algorithm, the vacuum power in the middle will be increased to suck those things little bit high. And also we adjust the brush speed based on the objects over there. As you can see, we have done like different, like in some wet settings. In front, it has two brushes like this. In middle, it has a roller and a vacuum mechanism. It can avoid humans. So sometimes when we do the when we discuss with some cleaning people, they suggested like when we move the robot from one place to another, instead of like operating through joystick, it is easy them to follow the, if we make it following that person. So we have done, and also we have developed like cloud-based inspection system. That means even the robot can be monitored from a far away location. And this robot is fixed with a standard 120-liter bin. As you can see it, we can lift down the bin and remove it after it full. Then also it has the autonomous docking facility for charging. So when we move in from the indoor to outdoor, it is not just change of the weather condition. It changed the whole things into a new dimension. Like in outdoor setting, there can be a lot of people. Like for example, when we are doing in a cleaning in, if we deploy the robot in a park, apart from the pedestrian who walks, there can be cyclists who move very fast, and also the audience also different. Like in roadside, there can be other vehicles. So autonomy and decision making should be more stable and more safety directed. For example, if somebody come in front of the robot, if it is less than 0.8 meter or something, regulation says the robot need to immediately stop, and the distance between the people and the robot should be less than some threshold value. Otherwise, we cannot deploy it in public space, because this robot is large, and it is enough just for like same as size of a vehicle. And I think I cannot remember the exact weight, close to maybe 500 or 600 kgs. So we have to have new algorithms which are useful for outdoor setting, and also in rain conditions. Sometimes once we did some field trial in a park and suddenly start to rain. What happens is with the rain, LiDAR sensors get issues with detecting, because LiDAR sensors start to detect rain particle as obstacles. So then robot should move to a side, and we need to make some algorithm to autonomously robot go and stop until the rain is in. So that's about the Panthera outdoor sweeping robot. So now I'm moving to the next one. And as similar to Sri Lanka, Singapore also facing issues with mosquitoes, like dengue cases are also increasing. So typically, routine fumigation is done in most of the residential places, and especially in construction site where there is stagnant water in construction site. So this fumigation, the main issue is it is health hazard for the person who are uh, doing the manual fumigation task, even though they use mask. If long-term exposure can cause some health risk. So we have developed a robotic system, this one especially for construction site, with a track-based mechanism and a fumigation unit that can move through uneven terrain and do the fumigation task. Here you can see. So we have named it as wombat misting. It can do misting and fumigation. So this was in done in a construction site in Singapore. First, here we can see the testing of the locomotion mechanism, because we use a track mechanism, and if we consider about real construction site, it appear like this mud, gravel, and this kind of bumps robot need to go through. Then damp gravel, it should be able. Now you can see the misting unit is activated, it rotated and do the misting. Due to actually some regulation issue, we haven't used the actual fumigation agent. Here we are only using the water. So in this kind of things, sometimes the robot might not be need to be a fully autonomy. Sometimes if even the robot we make it as a teleoperated robot which can be operated from a faraway place is sufficient, because it avoid the getting into hazardous exposure to hazardous chemical by the operator. So this is a little bit some ongoing work. So we have developed a robot for some gardening application. You know that if there are small saplings of vine-like plants, we need to use some stick, and we need to stake the plant to that stick. So one of the problem is when we use a robot to uh, grab the plant and move it toward the stick and use another arm to clip it. When we grab the plant, we need to robot need to grab it in the proper location with the proper force. Otherwise, it will damage the plant. So here, the however, the predicting the plant is very difficult because it has deformation probabilities. So when we touch from one end, how the other end deform, those kind of things we need to predict. We have developed like belief-based method for that one. So as here you can see some, or we have done only laboratory experiment for this one. You can see one robot arm is grabbing the plant and it is moved toward the stick, and the other robot arm is moving the staking device. Then it stakes it. So we have a benchmark with existing algorithm and our one. So this the our one can properly do, but without belief, it might grab from a different location. And now you can see in the right side, it misses the proper attachment to the stick. So pot was lifted, in that case too much force, it might can damage the roots of the plant. So the main problem of having autonomy for this kind of things in wild situations, in like plants and those kind of things, you cannot see the same object twice. Each object is unique. So we need to have good models that can replicate the behavior of those things. It is the most difficult and challenging task. So if we can have that one, like how to model these plants with their behavior to fully extend, then we can have a good reliable autonomy. Okay, this is the currently I'm working on this project. We are developing a housekeeping robot using vision language models. So in everywhere, hotels are in everywhere, in Singapore, in Sri Lanka, maybe Thailand. So one of the thing is after guests are leaving, the room need to the hotel staff need to make the room within a given limited time period. Maybe within 30 minutes they need to make a bed. And the one of the issue on that one is there are health concern like back injuries, and those things are common. So what we thought was like currently we are in the process of developing a hotel housekeeping robot for bed making. So to develop a large language model like visual language model, we need to have data. So in this case, what we are currently do is we are collecting a large set of human demonstration data. As you can see it here, we use like a 4 cameras. In the first one we use an external camera. Then the second view is we have mounted a camera in the head of the worker. So this is the view from the head. This is another camera moved in the left hand wrist, and this one is the right hand. So when then we ask the hotel staff to perform these tasks, and we collect human demonstration data. As you can see it here from camera, we can then we record these data. Then we do using algorithms, we use segmentations and identify what are the actions, and we store as labels, and we store them as a large data set. So then our belief is like our aim is to use these data and finally develop a vision language model that can autonomously handle the bed making task on that direction, we have done some preliminary work. Here you can see there's a inside the lab, we have created actually some bed and do the experiments. Here you can see a robot with manipulator. First, it analyze this environment and it decide how should it navigate toward a particular object and then to grab it and take it away. A little bit move it fast. So in this project, we are doing both, like we are collecting a large set of data set for making the robot, and also same time we are developing a new hardware system to do this task. Like because in a hotel setting, we need to tug the duet and those kind of things currently cannot be done with the existing robotic grippers. So even currently we have like advanced AI method like vision language model. We need to have proper hardware also, like how our grippers works and those kind of things. We need to have the proper embodiment usage, like we need to couple both hardware and also AI to have better performance. So when we discuss about this development I have shared, typically these robot address dirty, dull or dangerous tasks for humans. So where humans will face difficulty of doing these tasks, we can use this robot to uh, mitigate those issues. And here I need to like mention that we are not expecting like robot will replace the jobs of human, but what happened actually is it will improve the it will elevate the living standard of the current workers. Because let's say when we deploy this robot, it will also create a new set of jobs. For example, if we deploy a cleaning robot, the robot need to be done some maintenance. You need to remove the uh, beans, need to plug it for charging. If there is something happens, you need to do some small uh, maintenance tasks. For those kind of things also, it will create new job opportunities. So might be existing cleaner, we can give some training to these, do these kind of things. So likewise, we can elevate the living standard of human workers. And the other thing is like sometimes it is very difficult for human to work in confined spaces. Like it makes some kind of difficulties for the brain and also some breathing difficulties. So this robot deployment will ease those concerns of human. And also sometimes we do inspection tasks through humans. What happens is we do not have a proper recording. Sometimes the worker might go and say, oh, it's damaged, but how much it is damaged, where is the exact location, those kind of details are missing sometimes in the manual inspection. But if we use this kind of robot based inspection, we have some digital record, exact location, and what was the exact size of that one, where it was. Likewise, we can keep long-term records easily compared to the manual inspection time. So as I have mentioned earlier, like robot elevate the living standard and quality, not taking their jobs. So now I have previously mentioned about our research and development of robotics and AI system. Now I am going to discuss about the reality of robotics and AI in today context. So first, like if we consider about there is two different stories. Like for example, let's say software AI. You all know that like software AI system like maybe ChatGPT, Claude is currently used by million of people, and Those can be used for tasks like you can generate a report. For example, this presentation also I use some AI to generate. So that kind of things can be easily done using AI. After generating, we will do some modifications and make it the correction. If we consider about software AI, the main advantage in the software AI like ChatGPT, we have trillions of data to train them. In the internet, we have trillion of words and images to train networks. But if we consider about robots, we don't have such large amount of data to train a robot. That is one concern, one limitation. And if we consider software AI, then we can run them in massive GPU clusters. But in a robot, we have resource constraint. We cannot have a high powerful GPU. It might increase the cost of the robot and also weight of the robot and battery usage. So we have limited hardware computing resources. And the most important thing is, if we use software AI, typically the failures are reversible. Let's say when I generate this presentation, there were errors. I can create it. But if in the physical world, it's robot do something physically, reversing it back to the original state or correcting that one is difficult. So if we consider about these two different aspects, because most of the people think like things like ChatGPT can do things very efficient and perfect way. Why cannot robot do that way? That's the main issues that we are currently facing there. Genuinely, the software AI is at scale, but still robotics is still in the demonstrate stage. And even the ChatGPT can generate a report, but if we use the same ChatGPT to do a in a robot and asked to manipulate a coffee cup which is not previously seen to the robot, it might spill it. Still, the reliability is less. So the main limitation is the we don't have internet like large database for physical interaction. And also in environment settings are different lighting condition, different kind of layouts, different textures, and also robots are also not same. Like if we train a AI model in one particular robot, we cannot use that AI model in another new robot. So data collected on one platform might not be usable for another platform. And also the other things like dynamic friction and those things are also different. So when we think about like how we mitigate this bottleneck, actually we need to go within a layered way where we use simulation data for scaling, then we use simulation, then some synthetic data, we can use diversity, then finally we can use like first we use simulation, then use synthetic data for training, then do some teleoperation based operation and fine tune it. Likewise, we need to do it in layered architecture for improving the data for improving the robot learning and training paradigm. And also another thing currently people think like if we use bigger AI models will solve the robotics issue. Actually, it will not solve the issue. For an example, let's say we have like humanoid robots, and even if we use if we consider about existing humanoid robots, how many of robots have like human like hand, this hand and thumb? So this human thumb is the one of the mechanism that make the human the most advanced creature in the earth. So, but currently, if we consider about the existing robotic humanoid robots, we do not cannot see this kind of hands like sensing capabilities. So even though we improve the AI without having real hardware capabilities combined with the AI, we cannot have a high reliable operation. So the way to go forward is doing research in both AI and also hardware, and we need to select correct hardware entity and correct AI system to complement each other. And also when we deploy a robot for an application, we expect like 99% accuracy. We do not expect robot to be 90% because in a software or a report, if there is a mistake, it is a typo. But if it is a mistake in doing a robotic surgery or something, it is a catastrophic situation. So reliability is one of the metrics that we need to address when we do the robot deployments. Okay, next I'm going to discuss about the engineering trade-off between how we should move in future developments. So now I'm going to discuss about autonomy and supervisory control, especially in unknown environment. In initial days of we tried actually to have the full autonomy in robot, like eliminate the operator completely. Robot do the everything fully its own. But we found out that actually fully autonomy is not going to work in especially in unknown environment. In known environment, fine. For example, you can see robot taxis in USA, but those are mapped 1,000 times in those environment and work perfectly in mapped environment. But if we bring that car into a road in Sri Lanka or some other place, it will not work. So therefore, we currently argue that we need to have like autonomy plus human supervision. Like main task robot handle, like 90% of task is handled by the robot and 10% surprising situation is handled by the teleoperation. That means when the robot, maybe let's say we deploy 10 cleaning robots in different location, there can be one operator who continuously monitor those 10 robots. If suddenly something happen, this autonomous system automatically triggers the assistant of the human operator to take some actions. That kind of paradigms will be one of the easiest solution in the current state of the art. In 5 years, those may be different. In 5 years, there can be fully autonomous system. I mean, in the current time, at the moment, we need to go with a mixture of full autonomy and some shared autonomy concepts. And also another trade-off is how we develop robotic system. Typically, everybody like to have a robot that can perform all tasks. For example, let's say for our home, one of our home, let's say we have a robot that can do cleaning, then cooking, maybe washing. But let's say that robot only do every task, maybe 80% accuracy, or like 80% reliability, clean like 80% and some things are still there, and when cooking it's not properly cooking, like only 80%, and maybe washing also 80%. But people do not prefer to have that kind of system which only do 80%. So at the current situation, therefore mainly the people are preferring to develop task specific development. We can develop a robot to have cleaning efficiency of maybe over 95%, cooking maybe 95%, and washing maybe 95%. People like to use 3 different robots if those robots can do maybe 99% accuracy, reliability. If robot do those three different robot those 3 tasks with 99% reliability, people will go with that way, not with a single robot who perform 80% for each task. So generality is not the way to like, we do not need to consider generalized general purpose robot for the all goals. For some of the application, we need to have like dedicated robot will be sufficient and also more reliable. Like if we are doing a inspection task, that robot can do that inspection only might be sufficient. So mainly the current most development are focusing on task specific reality, and AI system and those things are very good on task specific context. No, even though those are not good in the generalized context. And the other thing is from lab to field. In laboratory testing, we use accuracy, precision, and some benchmark testing. Then we verify the algorithm. Then we analyze the performance comparing different methods. Then we use some statistical measures, repeatability, how is the confidence level. And but when we deploy in the real world setting, we need to complement it with robustness under different weather condition, dust, and also some unexpected situation like what happens during a rain, or somebody come and push the robot, how it should maintain stability. And let's say if we deploy a robot and we get some maintenance, how long should be the interval between those maintenance tasks? If the robot failed, how could it recover? And the other main thing is the usability. We cannot expect like field deployed robots are always operated by skilled engineers or researchers. So we need to make some systems that can improve the usability, how to operate the robot, how to configure it, how to change its parameters, those kind of things. We need to have some user interface that facilitates the non-expert operations. Then finally, like we need to integrate these things with human workflow. Even though we have developed good robotic system, we need to integrate this robotic system with the existing workflow. For example, if there is a building maintenance task, there is a existing protocol how human workers do that task. So when we integrate a robot, we need to have a smooth flow in that task. We cannot just remove some people and just put the robot, because in the flow should be like, for example, let's say there's a cleaning team who do the cleaning, but we replace this cleaning team and put a robot. But that cleaning team doesn't have any expert to do the robot maintenance task, small task even. So in that case, it might lead to a failure, because if the robot fails to a small issue, nobody there to fix that one. And also our design should target for the operator, not for the engineer who built it. For example, for when we develop some robot in laboratory, we sometimes use like to run the robot, we have to run 2, 3 scripts in the Linux, but in real deployment, we need to use some more initiative interfaces which are easily readable by non-expert. And also the other thing is like we need to ensure the trust before deploying the robot to the environment. First, we need to do some field trial and get some suggestion from the those existing maybe maintenance crew, and do some performance tuning, and need to maintain the expectation of the end users. And also we need to another main thing is we need to plan for the failure moves. Robot can fail, their sensors can fail, they might uh, these failures will lead to some, let's say, facade inspection. The robot fail for maybe some sensor burnout and need to order a new sensor. It take maybe 2 weeks, and if the maintenance inspection task need to hold it for 2 weeks, it might be a problematic. So need to have proper supply chains and maintenance system and service agreement with the robotic manufacturing companies and the end users. So now I'm going to discuss about opportunities for engineers to conclude my work. So now this is how the field is going on. Currently, the most of the robotics and AI is trending toward vision language action models. We call as VLAs. So vision language action models combines the perception, reasoning, and the control into a single model. So it sees the image and the output will be directly the robot actions like joint movement of a robot. So to this one, we need to have a good robotic hardware system and an AI system which train with a good set of data. And use of foundation model, the VLA is also a subset of foundation model. Currently the foundation models are also widely used, like maybe ChatGPT, Claude, Gemini, Lava. We can integrate those existing pre-trained model with robotic system for decision making to identify what is this context, what it need to do, that kind of things. Then one of the new direction is world models and predictive learning. Uh, World model and predictive learning, where robot models the world. It has a model of the world. Before executing an action, it simulate what will happen. Then it can fine tune and predict its action, and it fine tune its internal before doing the actual action. And the other thing is now when we do training and those things, we do it in simulation system like ISEC sim, NVIDIA ISEC sim, and if we change the from simulator to real environment, there is a gap. We need to like fill that gap. That is also one of the ongoing research direction, and also finally the ongoing inference, because even though sometimes we run it in a computer with a large GPU power, but in a robot we do not have that much of GPU power to run a AI algorithm. So we need to think how we can reduce the computational requirement of these AI systems. So this is about like context in Sri Lanka, since I have been in Sri Lanka for doing robotics in Sri Lanka also. So in Sri Lanka, we have like a lot of domain problem, like in plantation, sometimes irrigation networks, some blockades, how to identify those kind, then port infrastructures, then public transport. So in Sri Lanka also in industry, we can see many inspection and maintenance challenges. So that mirror the everything I discussed earlier. And also from the other hand, in Sri Lanka, we have mechanical, electrical, and computing, and also mathematical fundamentals are well taught in Sri Lanka in engineering degrees. And robotic and research is require exactly those kind of skills. Like when we do robotics and AI developments, we need to have mathematical foundations, computing, mechanical, electrical, such kind of knowledge. Those are already in Sri Lanka. And robotics group in like in here Singapore and also in UK and other countries are looking like partners. Sometimes we can collaborate to have to solve these kind of real world problems. So there are a lot of opportunities also within Sri Lanka to contribute to the maintenance and inspection task and improve those maintenance and inspection reliability using robotics and AI systems. So with this one, with this final takeaway, I will end my presentation. Typically, when we do robotic demonstration, those are very well work. Like example, you may have seen some robot jumping, dancing, doing many tasks. Most of those tasks are like properly choreographic tasks, not in unstructured or unknown environment. But if we deploy that one in a real unknown environment, deployment is highly challenging. To close this gap, we need to like complement like research, engineering, and operation all at once. So everybody need to contribute, and then we can try to solve these problems. With this final remark, I am ending my presentation. Thank you very much.
Thank you, Dr. Viraj Muthugala, for that insightful session. I believe that our participants gained deep knowledge on this topic. Now we will move on to the Q&A session. Participants can now ask questions either by unmuting your mic or by sending a message in the chat box. So we have a question asked in the chat box. How about the idea of using PIC for cleaning robots instead of LiDAR?
Okay, PIC. What is exactly PIC means?
I'm not sure. PIC or PS? It's mentioned as PIC. Question.
I see.
Programmable ICs.
Okay, programmable license. All right. So instead of LiDAR, all right. So typically in a cleaning robot, like it depends on what kind of sensors we used and the control algorithm we are going to use in the robot. So let's say robotics have some primarily sensors like IR sensors, sonar sensors, and doesn't have a large AI model. We can go with like embedded programmable ICs like maybe uh, Arduino or PIC like ICs. And but if we use like vision system and LiDAR like sensors, we need like if we use a LiDAR, we need to create a map of the environment to create mapping or do vision based object identification or navigation. For such kind of things we need to have higher processing power. For such cases we need to have like computer like thing like single board computers like Raspberry Pi or that kind of devices which can do some image processing, handle LiDAR, and also run AI based algorithms. I think that will answer my that will answer Chandana's question, I think. Yes.
Another question raised is gaps recently in robotics.
That's a very good question, and gaps recently in robotics. So like in these days, we can see mostly the development of AI systems. Like every day, you can heard like ChatGPT can pass the medical exam, then another new AI can do this task. And but when we deploy, let's say, same AI model for a robot, we cannot have the same level of performance. Because in a robotic system we need to have like two different layers. One is perception. We need to identify the situation, then we need to know some decision making. Finally those decision making lead to control of these actuators. When we consider about this general purpose AI like ChatGPT, those have many trillions of data in internet to train, like books, research reports, web pages, images. But when we move into the robotics, we need to have, if we want to have same level of performance, we need to have like, let's say this the environment setting, this should be the moving angle of each joint for a robot. If we have that kind of large data set, trillions of data similar to the internet, we can have a robotic system with fully AI capabilities. That is one of the real gaps. The second real gaps of having AI in robot is the resource scarcity. We cannot have like large GPU powered computers in robots because we have limited size and also battery power. We have to tackle with those kind of scenarios. Those are the mainly the reasons gaps in robotics.
All participants, if you have any questions, you can unmute yourselves and ask directly also. Um, the next question we have in the chat box is, in robotic developments, do you consider ergonomics?
Okay, in robotics development, typically we do consider ergonomics also. It is two different approaches. When we develop these robots, those robots should be human friendly because finally the users are humans. So our interfaces and those things should be ergonomically friendly. Otherwise, nobody will like to operate the robot. And for an example, like other things also like that. For an example, in the that outdoor sweeping robot case, we have like a bin. That bin is automatically lifted by the robot to the ground, and user just need to uh, pull it without much force. So those things will ensure the human ergonomics when we make the robot to but in the things like maintenance and those kind of things, when a person is going to maintain a robot, it might not be ergonomically friendly yet. We haven't considered those kind of things, but we make the like outer shape to ensure the human safety and ergonomics when moving through humans. We develop like algorithms that can blend with humans while moving in crowded spaces. In such kind of things, we consider the human ergonomics.
I hope it answered the question. And
There's
the next
another.
one is, what are the single board computers used for outdoor cleaning robot and staircase climbing robot? The next part is, are there multiple processors used?
Uh, okay, so in the that outdoor cleaning robot, actually it had like three industrial PCs. So one for because it the outdoor robot Panthera, it's bit large and safety is one of the critical aspect. It had like three 3D lidars. Typically in a 3D lidar we get a massive point cloud from each lidar. So one is used to handle those kind of lidar sensors, and we had another industrial PC with GPU to do the high level to run high level algorithms. And third, we had another industrial PC which coordinate with the basic motor drivers and those kind of peripheral sensors with those two computers. Typically we need to use like multiple computers, and also those computers are not in that large robot. Those are way powerful than the single board computers like Raspberry Pi, more like industrial grade, like similar to normal PCs, but with small form factor with industrial grade vibration and temperature handling capabilities.
The next question is, can you please give examples of latest successful advanced robotics projects like humanoid robots in China and Boston Dynamic Robotics Law?
Okay, in yeah, that's a good question because these days we can see a boom of humanoid robots in China like Unitree and Booster Robotics. We can see many humanoid robots, and also if we check their prices are also quite low, like $16,000 is for a humanoid robot, which is quite cheap when we consider about other European and US based. Like previously it was like 3-4 times higher than that amount. So now in China, the the cost of development of this hardware platform are getting cheaper, and people have from the other end, the others like Singapore, maybe Sri Lanka, maybe other countries have access to this hardware in a reasonable pricing tag to do the further development. Then on the other hand, if we consider about like Boston Dynamic robotic dog, we can see similar type of dogs also from Chinese manufacturer. Like Unitree have a like costly around I think 2000 Singapore dollar or something. We can get a human this dog like robot. So those hardware are becoming cheaper, and also the accessibility for the hardware from is also increasing. But the problem is, even though we can see many humanoid robot development, but still these humanoid robot developments are mostly targeted for demonstration purposes. Still, we cannot have a proper generalized robot that can do like all household tasks in like untrained environment. It might work in a previously known task can do, but in a completely unknown environment, still the AI and these project development are not up to that standard.
The next question is, what is the current feasibility and market tendency towards AI solutions in Singapore, and how can these solutions be adapted to the Sri Lankan industry?
Okay, feasibility and market. Okay, that's a good question. Currently, like in worldwide, we can see a boom of AI solutions. In Singapore also, like as you can see in US government is pumping some amount of money, and also similarly Singapore government also putting millions of dollars to universities and research institute and also industries to do AI development. So when we consider about like industrial development, there are still most of the things are done in like in manual labor intensive inspection. If we consider about facade inspection, those are still manual. Then ship inspection tasks, aircraft, and those kind of things are still going on manual. And currently, like we are just undertaking a new project in aircraft baggage handling. Currently, aircraft baggage handling is done in manual things like people lift and throw the baggage. But currently, we are developing like AI-based robotic system to grab bags and put to the trolleys, that kind of systems. So likewise, the AI is booming, and everybody is adapting these AI system to their industries. For an example, sometimes we do not need to do the full scale end-to-end AI development. Sometimes we can use an existing AI model with some open weights and fine tune it for our application. Because development of like a foundation model like ChatGPT or Lava from scratch to end is a difficult and also time consuming and resource constrained task. Mostly the easiest way is the use the existing system and customize it and adapt it to our usage. When we consider about the Sri Lankan context, there are different industries like similar to here in Sri Lanka also we have high-rise buildings and need to do facade cleaning. Currently, it is manual process, and even in Sri Lanka, we find labor shortages, skilled labor. So we need to think about how we integrate these robot into the industry and how we can have a smooth transition of using these robot, because sometimes especially in developing world when we mention like we are going to use robot for this one, the common perception of those workers will be like robot are taking their jobs. For an like in sometimes like as I could remember in like when I attended a conference in India in Delhi, like an immigration officer in Delhi airport asked me why are you arriving to Delhi. So I told like I'm attending this robotic conference. Then he asked, "How you guys are going to, how many jobs you guys are going to take using robots?" So sometimes these some common mans have that kind of perceptions. So actually use of these robots in industrial application will not take over the jobs. Actually, it will improve the living standard and the quality of maintenance and inspection task. We have to have a smooth transition on that aspect, as well as we need to integrate this robotic solution to the existing workflow. Like we cannot have a robot with a maintenance crew who don't have any knowledge about robots. We have to either train them to operate robot, do some pre-training, and like a wise of situation we have to do before adapting the robot to the industry. I hope that we answer that answer the question.
So seems like there's no any other questions being raised. Anybody else can ask a question? So it seems like that's the end of the questions being asked.
Right. Thank you everybody for joining with me on this presentation, and especially I am thanking IESL Electrical, Electronics and Telecommunication Engineering Sectional Committee for inviting me. Thank you.
Thank you for all those questions. I hope that all your questions were well answered by Dr. Viraj. Uh, so I would like to invite Engineer Sapumal Valisundara, Operations Team Lead, IESL Electrical, Electronics and Telecommunication Engineering Sectional Committee, to deliver the vote of thanks. Over to you, Engineer Sapumal.
Good evening, ladies and gentlemen. As we conclude this timely session, I would like to formally propose the vote of thanks on behalf of IESL, Electronic and Telecommunication Engineering Sectional Committee. So first, our sincere gratitude goes to our resource person, Dr. Viraj Muthugala, for the brilliant presentation. Thank you for sharing your expertise on AI-driven inspection and giving us practical strategies to solve real-world industrial problems. Next, I thank President of IESL, Engineer Kosala Kamradini, and the IESL Council for their leadership and constant support towards our committee's initiatives. And also, I must acknowledge our chairman of sectional committee, Engineer Viraj Muthugala, along with the hardworking EETESC sectional committee organizing team and for conceptualizing and executing tonight's event. And our thanks also goes to IESL Secretariat for handling the smooth back-end coordination and digital logistics for this webinar. Finally, thank to all of our participants, engineers, professionals, and students for your active attendance and engagement what make those knowledge sharing sessions success. And thank you everyone. We'll meet in on the next technical session. So until that, have a safe and wonderful time. Thank you again.